This problem is to solve for a BJT differential amplifier that is being driven by a current source. Note that this current source has two currents that are being generated. One is here and one is here. The problem wants to find the differential input resistance RID, the gain VO1 over VID, Cmrr, and the range for VO2. It's given to design it for GM equal to 20 milliamp per volt. And so starting with RID is going to be the pathway from the one side of VB1 to VB2. So this would be the positive, and then the pathway would go through till you get to the other side of VB2. So drawing this portion of the hybrid pi, I'm going to call this Q1, Q2. Not really going to be concerned with what's happening up there because there's no connection from there back to this pathway. Same thing here. And this is the VB2 side. So the path goes through RPi1 back through the RPi2. These are also connected, so we have to get rid of those. To get rid of this one, which is attached to this one, you would multiply that transistor by beta plus 1. And then for this one, you would divide. And those would end up canceling to give you RID equal to 2 RPi. RPi is related to GM by beta over GM. So this ends up giving 10K. The next step is to find the gain VO1 over VID. VO1, which is located here, has this, which is RO2, or RO, whatever RO resistance is of that one. This one, which is RO2, and then whatever's seen over here for the Darlington. So drawing the Darlington portion to find the equivalent resistance at VO1. So we want to find an R equivalent here. We know we're going to have to use this current to find some of the variables here. So we need to find the currents. Again, we'll use GM to find that. GM is 20 milli is equal to IC over VT, which is 25 milli, which gives an IC of 0.5 milliamps. This is the current flowing through the transistors up here. So 0.5 milli and 0.5 milli. So the total current would be 2 times that. Down here would be 1 milli. And then knowing that this is a Wilson, the Wilson relates the I naught to the I ref, where this is considered I naught over here, and this would be your I ref portion, as 1 over 1 plus 2 over beta squared. Multiplying this out, it ends up being 0.998, which is really, really small, and so will not be a factor, and so I naught will equal I ref in this example for the Wilson, and that's the benefit of the Wilson. It's more accurate than the simple BJTDiffAmp. So this one is pretty close to 1 milliamp, so I'm going to assume it is. And I know it's being reflected here. Again, it's a BJT, and it's a simple current mirror. So the simple current mirror is 1 over 2 times beta. In this case, I naught is this current of 1 milli. And we want to know this current now. I'll call it I1, which will be here. So the relationship between the 1 milli and I1. Solving this for I1 gives 1.02 milliamps. So it's still pretty close to 1. Since this is the same reflection over here, this is also going to be 1 milliamp. So now I know all of my currents. I'm going to draw the hybrid pi for the Darlington portion to find that R equivalent. The problem also, I was told to ignore the early voltage for the Darlington transistors. So I'm going to call this 3 and this one 4. So R pi 3, R pi 4. And the equivalent resistance for this one is going to be R naught So now I want to find the equivalent resistance. So I need to get rid of these dependent sources so that I can take an equivalent pathway of just the resistances. So I'm coming in at the base, so I'm going to reflect everything in the emitter side by multiplying it by beta plus 1. And again here, my pathway comes down through here in this direction, so this will then be again multiplied by beta plus 1 squared. So the R equivalent is R pi 3 plus R pi 4 times beta plus 1 and then plus R naught times beta plus 1 squared. Now to find the R pi's, I need to go back and find the DC currents. I know that 1 milliamp is biasing the Darlington, so I can reflect that into the base current. IB4 is going to be 1 milli divided by 101. That's 10 micro. That's the same as IE3. That's the current in the emitter for transistor 3. And then I can use the relationship again to get IB3, which is IE3 over 101. So I end up with 99 nanoamps for this one. So I can find R pi's from that. R pi 3 will be VT over IB3. So 25 milli over 99 nano. And that gives a value of 252,500. And R pi 4 is VT over IB4, 25 milli over 10 micro, for a value of 2.5K. So plugging that back in here, I also need to know RO. RO is going to be VA over the current flow going through the transistor, and so that's going to be again 1 milli. So now plugging these all back in, the R equivalent comes out to be approximately 50 or 500 megs. So our equivalent is just looking into the Darlington portion. So to find the gain is going to be the resistance here in parallel with that resistance in parallel with this resistance. So the overall gain is 1/2 GM RO in parallel with RO in parallel with the R equivalent. Now these ROs are the ROs in the differential amplifier. So both of these have the same value of VA over 0.5 milli. And this again was what we started with, which is 20 milli. So multiplying that out, it ends up giving a value of approximately 1K volt per volt. I'm just finding the magnitude of this. So 1K volt per volt. The next thing to find is the CMRR. The CMRR for this active loaded differential BJT amplifier is 1/2 beta GMREE. This again is 20 milli, and we need to find REE. REE is the equivalent resistance seen for this bottom current source down here. So that's going to be the output resistance of the Wilson mirror, which is beta RO over 2. And RO again is the RO for this, which has a current flow of 1 milli. So it's over 1 milli divided by 2, which is 1.25 K. And that gives a CMRR of approximately 1.25 K. Now the last part of this problem is to find the range for VO2, which is on the output of the Darlington. So that's going to be determined by the pathways from the negative up to that point and then from the positive down. So the max will be from the positive side. So I also know across these there's a minimum that I have to have, which will be 0.3. I also know the drops across VBE of 0.7. And again down here, this is 0.3. So my max is going to be 15 minus. I note that if I go through just the Q4 of minus 0.3, that the difference between those 2 points is not going to be enough to keep this one also at 0.3. So I'm going to have to take the pathway instead through Q3. So it will be 0.3 minus 0.7, which ends up being 14 volts. And the min is from the bottom, minus 15, going through this, plus 0.3 is a minus 14.7. So writing these down again as a summary, RID was 10K, VO1 over VID, the magnitude of it was 1K volt per volt. The CMRR, 1.25K, and the range for VO2, 14 minus 14.7.